In the past two lectures, we have talked about the elementary steps that make up most reaction mechanisms. However, many mechanisms have multiple steps before they reach a desired product. A great example of this is the unimolecular nucleophilic substitution reaction, SN1. Unlike a bimolecular nucleophilic substitution reaction, SN2, SN1 reactions proceed as two distinct steps. Take a moment and see if you can name these two steps by looking at the SN1 mechanism shown. The first step is a heterolysis, and the second step is a coordination step. Notice that the heterolysis always has to take place first. We can have an incomplete octet, which will be higher in energy but still achievable. However, under no circumstances can carbon have more than 8 electrons, so heterolysis will always occur first and then coordination. Even though these steps are demonstrably distinct, we rarely can isolate the middle step, called an intermediate. We can tell that it is formed from other evidence, but usually cannot actually see it. Think about the shape of the reaction coordinate diagram. We start out with a negatively charged nucleophile and a neutrally charged electrophile, so one negative charge, one neutral charge. The product also has one negative charge and one neutral charge. The intermediate, on the other hand, has 3 charges and one incomplete octet. We have a positively charged carbocation, we have a negatively charged leaving group, and we have a negatively charged nucleophile. So because of all these charges and the incomplete octet, we'll have a much higher energy intermediate than the reactant or the product. I didn't want to show you this until after you thought about what the reaction coordinate diagram would look like on the last slide, but now again you can clearly see the 3 charges in the intermediate and the incomplete octet will make the carbocation intermediate much less stable and therefore very difficult to isolate. Just like we can have a unimolecular substitution or a bimolecular substitution, we can also have a unimolecular elimination mechanism that goes through 2 steps. Once again, look at those 2 steps shown below and try to identify what each of the elementary steps are. The E1 mechanism, just like the SN1 mechanism, begins with a heterolysis step. After the heterolysis step, the next step is a proton transfer reaction in a unimolecular elimination reaction. I've mentioned several times now that it is incredibly rare to see the carbocations directly. For a long time, only indirect evidence indicated the presence of carbocations. However, George Olah was able to isolate carbocations using magic acid, which is a superacid. It's shown on the bottom of this slide. George Olah isolated the additional carbocations and received a Nobel Prize for this work. We can see why this was so difficult to isolate if we look at the reaction coordinate diagram for an E1 or an SN1 reaction. I have an SN1 reaction shown here. Remember that the rate constant of a reaction is largely dependent on the activation energy of a reaction. A lower activation energy means faster, and the overall rate of reaction is a function of the rate constant and all of its participants. So for the first step, a heterolysis, we know that we're going to have a much less stable set of products, which means the activation energy is going to be high and the reaction slow. On the other hand, going from a carbocation through a coordination step results in a much lower energy set of products, and therefore a low activation energy and a faster reaction. If the first reactant is slow and the second is fast, we say the first reaction is rate limiting. The second reaction cannot go any faster than the first reaction, since it will quickly run out of reactants then. Therefore, the rate of the entire reaction, this entire substitution reaction, amounts to the rate of just the first reaction. One final thing to note, if the rate of the overall reaction is only based on the rate of the heterolysis step, we know that the rate will be independent of the concentration of nucleophile. The rate limiting step only has the leaving group compound. Nucleophile doesn't participate in the rate limiting step and is therefore irrelevant to rate for an SN1 reaction. We can actually look at different rates of reactions with response to changing base or nucleophile concentration to tell us indirectly about the mechanism by which a molecule reacts. For example, the rate-limiting step of E1 reactions is the heterolysis step, and the rate only depends on the concentration of the molecule with the leaving group. Likewise, SN1 reactions are also limited only by the concentration of the electrophile with the leaving group. On the other hand, E2 reactions depend on base concentration along with the concentration of the molecule with the leaving group, and SN2 reactions depend on both nucleophile and electrophile concentrations. So if we increase the amount of nucleophile or base that a reaction is run with, we can see whether the rate of the reaction is going to increase or stay the same. If we have no change in the rate as we increase the concentration of the base or the nucleophile, that's going to indicate that we have a unimolecular, like an E1 or an SN1 mechanism. While if we double the base or nucleophile concentration and we see a doubled rate, that would indicate an E2 or an SN2 mechanism. What do you think would be indicated by an increase of rate that's only 1.5 times in an experiment where we doubled the base or nucleophile? Try to answer this question and then bring the answer to class. If we want to get more of any reaction to go, remember that molecules have more energy with an increased temperature. The higher the temperature, the higher the fraction of molecules that are above the activation energy, and therefore the faster the reaction can proceed. The Arrhenius equation from GenChem gives a numerical description for this. Notice that T shows up in two separate places in the equation, T for temperature. It reduces the effect of the exponential term by making the exponent closer to 0 as T increases, and therefore makes E closer to 1, that term closer to 1. It also has a multiplicative effect outside of the exponential term. All this to say that heating up a reaction will pretty much always make it go faster, no matter what the reaction type. We've just talked about how to tell if a reaction is unimolecular or bimolecular by the rate. We can also tell, particularly with the substitution, which mechanisms occur by the products formed. Think about the planar carbocation that is an intermediate in unimolecular reactions. The coordination step that occurs afterwards has no reason to occur from one side or another, because that molecule is completely flat. So a racemic mixture of enantiomers is always formed, an equal mixture of both the R and S enantiomers. It may be useful to try to envision most of the molecule in a plane, and the nucleophile attacking from one side or the other. The side that it attacks from will determine the chirality. This is distinctly different than bimolecular reactions, which require the nucleophile to come in from the opposite side of the leaving group, and are therefore very controlled. More on this in a little bit. While unimolecular reactions generally will form racemates, equal mixtures of enantiomers, chirality that occurs near the carbocation can actually change the likelihood of a nucleophile to approach from one side or the other. Two diastereomers are possible in this case, but they will be formed in unequal ratios. This is just like we saw in Lab 6, where we methylated benzoin to form one diastereomer over the other. We just saw that reactions with unimolecular substitution mechanisms will give mixtures of products. The reaction shown here proceeds by a bimolecular substitution. Notice that the iodine ends up only on the opposite side from the chlorine that left. Only one stereoisomer is formed. Let's pin that. There are a couple of ways to explain that stereospecificity, one of which we've already talked about. For the HOMO, the highest occupied molecular orbital of a nucleophile, to interact with the lowest unoccupied molecular orbital of the carbon leaving group bond, it needs to be coming from the opposite side. So we know that we're going to get an inversion of that stereochemistry. We could hypothetically imagine two ways of bringing in a nucleophile when the leaving group leaves. Obviously, we just talked about the molecular orbital theory picture of this mechanism, which shows that the frontier molecular orbitals, the HOMO and LUMO, only align when the nucleophile comes in from the opposite side as the leaving group. Even if this wasn't the case, attack from the opposite side minimizes steric strain. and electronic repulsion, which both offer significant barriers if we attacked from the same side. Because the iodine needs to come in at the same time as the chlorine leaves, the stereochemistry is absolutely going to be controlled in these cases. We say that the stereocenter is inverted. In many cases, SN2 reactions are preferred because of this stereospecificity, that is, the tendency to form only one stereoisomer. This charge density map shows the repulsion even more clearly. Since the leaving groups and nucleophiles are both negative, red in this diagram, they would repel each other. However, attack from the opposite side would result in interaction between the nucleophile and the positive side of the dipole created by the carbon leaving group bond. Negative and positive is a much more likely interaction, so we always see attack from the opposite side. We have similar considerations when eliminations occur. Although generally no new stereocenters are formed, and in many cases stereocenters are eliminated, however, EZ conformers are diastereomers of each other, and often one diastereomer will form preferentially to the other. In this case, the E isomer is much preferred to the Z isomer. This makes sense mechanistically because the carbocation is formed first and can rotate around freely in most cases. The most stable conformation will be the form the molecule takes most of the time, leading to a product that generally has less steric strain. However, this is a stereoselective process, not stereospecific. The E form is preferred to the Z form, but because some portion of the molecules will have the aromatics on the same side at any given time, some Z is still formed. If we go through an E2 reaction instead, the reaction is now stereospecific. Only one diastereomer will form, and it has nothing to do with the orientation of the aromatics. Instead, it has everything to do with the orientation of the hydrogen relative to the leaving group. We talked about this a little bit when we talked about molecular orbitals. Again, this molecular orbital description is a powerful tool to help us understand this preference. When the acidic hydrogen is anti to the leaving group, the HOMO and LUMO are physically close and the electrons can easily form a pi bond to the carbon leaving group, LUMO, while kicking out the LUMO at the same time. When they are not physically close, now this hydrogen isn't nearly as acidic and the reaction won't proceed. Looking back at our original example, there is exactly one conformation where the acidic hydrogen and bromine are anti, and the product is essentially a flattened out version of just this conformation. So we know that we need our hydrogen and bromine to be anti to each other, and that's going to drive which conformation we see. There are two words that we use to describe the relationship between the acidic hydrogen and the leaving group: anticoplanar or antiperiplanar. They both mean the same thing. Both the hydrogen and the leaving group are simultaneously removed from these arrangements, forcing both of the carbons involved to become trigonal planar at the exact same time and locking all the other substituents into a flattened version of the conformation they were in. However, sometimes there are multiple hydrogens that could be antiperiplanar or anticoplanar to the leaving group. Generally, forming a more substituted double bond is more stable. This figure from your text completely ignores the possibility of removing hydrogens from the adjacent methyl for this reason. We just don't see monosubstituted alkenes form when we could form disubstituted alkenes instead. So we know that it's going to be a 2-butene and it won't be a 1-butene. We also see that there are two hydrogens that would give us disubstituted alkenes, the 2-butene, but we get different products for each of those hydrogens. The reaction will be stereoselective towards the product formed from the more stable Newman projection, but will form a mixture of both products. We can see the Newman projections here. So the Newman projection on the left has Gaussian interactions between those methyls and will be less stable, even though it has an antiperiplanar hydrogen to that bromine. The Newman projection on the right has no Gaussian interactions, no steric interactions between the methyls, and still has a hydrogen antiperiplanar to the bromine. When this Newman projection, the right one, reacts, we'll end up with a more stable product. It is exceedingly common for a multi-step reaction to include a proton transfer reaction. These are fast and also ubiquitous, but we need to be careful to make sure that any acids or bases that are used and formed in the reaction are reasonable to see in a mechanism. If, for example, the reaction is in basic conditions, we cannot have a strong acid anywhere in the reaction. We know those would neutralize right away. This means that if we have a potassium hydroxide, like in the reaction shown, we cannot have a nucleophilic substitution reaction first, followed by a proton transfer reaction. The resulting protonated ether that's shown in the middle there is incompatible with the reaction conditions. Instead, we're going to deprotonate the alcohol with the strong base first. We'll have the proton transfer first, and then we'll have that serve as the nucleophile for the resulting substitution reaction. That way, when we're in base, we only see basic intermediates or neutral intermediates formed. We also need to remember that solvent is everywhere. A molecule can easily transfer protons to and from the solvent. It's tempting to think about a hydrogen moving from a positively charged location to a negatively charged location on the same molecule. However, we need to have contact for a proton transfer to occur. This is far more likely to happen with the solvent, which will be constantly in contact with each part of the molecule, than for the molecule to rotate around into the specific conformation to transfer a proton to itself. So we always draw proton transfers occurring with the solvent and never within the same molecule. Whenever we draw a multi-step mechanism, we also need to consider molecularity, that is, the number of molecules that are involved. As a review, reactions that involve one reactant are unimolecular. We see plenty of examples of these, like the heterolysis steps that begin SN1 and E1 mechanisms. Reactions that involve two reactant molecules are bimolecular, like SN2 and E2 mechanisms. Mechanisms that involve three molecules are termolecular. That means three molecules would have to simultaneously collide in the right orientation with sufficient energy for a termolecular reaction mechanism to occur. That doesn't happen. We need to draw reaction mechanisms as sequences of reactions that would actually occur, which never include termolecular mechanisms. It is also worth noting that 1,2 hydride shifts and 1,2 alkyl shifts are very fast, like proton transfers. If it is possible to stabilize a carbocation through a 1,2 shift, it will happen. We should assume this anytime we have a mechanism that involves a heterolysis, or anytime we see a mechanism that involves a carbocation. However, carbocations will never become less stable, which means that we will never shift a tertiary carbocation to make a secondary carbocation, as an example. We also don't have shifts over larger distances than adjacent carbons. 1,2 shifts are ubiquitous, they're all over the place, but 1,3 shifts don't really happen. So when we're drawing a reaction mechanism, we have to pay careful attention to stereochemical considerations. We also have to pay close attention to possible proton transfers and possible 1,2 hydride shifts.